everyone. Today we are going to see operating system unit 3 session 13. In the previous session we have studied what are deadlocks and which are the 4 necessary conditions to occur the deadlocks. In today's session we will study how to handle the deadlocks. So deadlocks occur when multiple processes trying to access the same resource. Like in an example we have seen dining philosopher's problem. We have seen the 5 philosophers trying to access the chopstick at the same time, then it creates the deadlock, as there are 5 philosophers and only 5 chopsticks. So these 5 chopsticks has to be shared among 5 philosophers, that everyone should get the chance to eat, so that they can coordinate, synchronize, and they can eat and think, and the system should, and everyone should get the chance, and they should not stuck. That is the same way in the system also. So when there are multiple processes trying to access the same resource, they should not get stuck, and they should share the resources in such a way that they should not enter into the deadlock, and everyone should get the chance to access the resource. So the operating system has to know about the deadlocks, whether the system has gone into the deadlock or no, so that the operating system can solve it. So there are 3 ways to handle the deadlock: deadlock detection and recovery, deadlock avoidance, and deadlock prevention. So first one we'll see deadlock detection. How can operating system detect deadlock when there is a deadlock occurs? So to detect deadlock, operating system has to know. So it's very important for the operating system to understand whether the system has gone in the deadlock or no. Some of the processes are stuck or no. So before occurring the deadlock, the operating system has to detect the deadlocks, and even if the deadlock occurs, how to solve it, how to handle that situation, the operating system has to know. So the operating system has to know current resource allocation, which process has which resource. So the operating system must have the knowledge about which resource is with which process. So there are multiple processes. As we have seen, there are 5 philosophers and 5 chopsticks. Then currently the chopstick is with whom? Means with philosopher 1 or 2 or 3. So that means which process has which resource. So this knowledge the operating system must have. And another knowledge is current request allocation. Which process is waiting for which resources. So some of the processes may request some additional resources. In the further needs, they want still resources to be used. So which processes are requesting which resource? Even this knowledge the operating system must have. Like now there are 5 philosophers and 5 chopsticks. So one of the philosopher is eating, then the neighbors of the philosopher should be not allowed to eat when the particular philosopher is eating. That means as there are only 5 chopsticks, so this chopstick has to be shared. So when a particular philosopher is eating, the neighbors philosophers has to keep on waiting, and when that philosopher finishes, the neighbor philosopher can get the chance to eat. So the processes, those who are waiting to eat, are like waiting for the resource. So this knowledge the operating system must have to detect the deadlock. So if they try to fulfill the demand of the processes, whether the system goes into the deadlock or no, this knowledge the operating system must have. This information can be used to detect deadlocks. So detection could work by finding cycles in resource allocation graph. So in the previous session we have studied about the resource allocation graph. So resource allocation graphs says that whether the processes or whether the operating systems are in a deadlock or no. So this circle represent processes and this rectangle represent resources. That means process B is using resource T, and T is allocated to E process, and process E is using V, and V is allocated to G process. Process G is using V. So like this way, this all processes are waiting for each other resources, and this creates a circular form or a circular wait. They are waiting for each other resources and the system goes into the deadlock. So resource allocation graphs tells us which resources are with which processes. So deadlock detection, as I told you, the operating system must have the knowledge about current allocation and request, that is current allocation matrix and request matrix. So let us understand what are this current allocation and request matrix with help of an example. So they are given some resources, like there are 4 tape drives, 2 plotters, 3 scanners and 1 Blu-rays. So out of these 4 tape drives, some of the tape drives are allocated to the processes. There are 3 processes here: process 1, process 2 and process 3. And there are 4 resources, tape drives. These are the tape drives, these are the plotters and scanners and Blu-rays. So some of the tape drives are allocated to the processes. See, 2 tape drives are allocated to process P2 and 1 plotter is allocated to process P3 and 1 scanner is allocated to process P1 and 2 scanners are allocated to process P3. You can see here 1 Blu-ray is allocated to process P2. So from this matrix we understood that which process is having which resource. So process P1, P2, P3 has allocated some resources, and now again they are requesting some new resources. So after allocation, these are the available resources. So from these available resources, can you fulfill the new demand of the processes? Can you allocate them the resources out of these remaining available resources? So you need to check here, so that you should allocate the resources to the processes in such a way that the system should not enter into a deadlock. So the tape drives, see, process 1 needs 2 tape drives, and how many tape drives are available here? 2 tape drives. So you can fulfill the demand of process P1, but here it is also requesting 1 Blu-ray, but Blu-rays are not available. There are 0 Blu-rays. That means currently you cannot fulfill the request of process P1. See, even if there are 2 tape drives but Blu-rays are not available, and process P1 is requesting that at a time and it is not available. So P1 demand cannot be satisfied, currently cannot be satisfied. And then process P2 is demanding 1 tape drive and 1 scanner. So how many tape drives are available? 2 tape drives are available, but there are no scanners. So even P2 you cannot fulfill the demand, current demand. And what about process P3? Process P3 is demanding 2 tape drives and 1 plotters. And you check here, 2 tape drives are available and 1 plotter is available. Yes, you can fulfill the demand of process P3. So in this new request matrix, you cannot fulfill the demand of process P1 also, P2 also, but you can fulfill the demand of process P3. So the system does not enter into the deadlock, because out of 3 processes you can fulfill the demand of at least 1 process. If you cannot fulfill the demand of all the 3 processes, then the system enters into the deadlock. So out of 3 processes, whatever they are requesting, you need to fulfill at least 1 process demand. Then the system does not enter into the deadlock. The same problem we have discussed here. See, this is the request current allocation matrix, request matrix. So P1 is requesting 2 tape drives and 1 Blu-rays, and which are not available. So P1 cannot be satisfied and even P2 cannot be satisfied, but we can satisfy process 3 demands, so no deadlock enters. So this is how the current allocation matrix and request matrix helps the operating system to detect the deadlock. Deadlock recovery. Now after detecting the deadlock is going to occur or has occurred, the operating system has to take some steps to recover from this deadlock. So first way is raise an alarm. Tell users and administrators that deadlock has been detected. So have you all observed or seen that whenever you are using the system or whenever you are operating the mobile phones, when you make some mistakes or errors, the system gives beeps, and from that beeps we need to understand that we are making a mistake. So at a time, so all the time if you keep on repeating the same mistakes, then system goes into the deadlock. So raise an alarm, it is like one alert that system can go into the deadlock if you repeat the same steps. Resource preemption. Take away a resource temporarily, forcefully stopping execution of process and given the chance to execute for other process. That means now suppose already the process is allocated to some resource is allocated to some process, and even another process is trying to use that resource, then there are chances of system going into the deadlock. So what you can do, the process which has lower priority, that process you can take the CPU from such process and you can give the CPU to higher priority process. Means forcefully you are stopping the execution of one process and you are giving it to another high priority process. So that the system should, you are doing this because operating system is doing this because the system should not enter into the deadlock. Rollback. Checkpoint states and then rollback. So we have seen that in the competitions, when there is a running race competitions, to check the health of the persons, there are checkpoints at different places. At different places checkpoints are located, and in this whenever the person reaches to these checkpoints, the person's health is checked up and then he can move to, then he can proceed. If he is already, then he can move further. If his health is damaging, then that process will be not allowed to proceed further. Same way here in the operating system, at every point there are checkpoints. So whenever a process is executing, the process there will be a sensing that means there is a checking that whether the operating system enters into the deadlock or no. So at every checkpoints, the operating system will check whether there are processes who are going to enter into the deadlock or no. If they are going to enter into the deadlock, then those processes will be stopped immediately and those will be rolled back to the previous state. We can understand this with the help of an diagram. See here, rollback. So these are the process execution. The process is executing and at some points there is a checkpoint. So at this checkpoint, whenever the process executes, whenever the process reaches, then at each checkpoint the processes are checked or the operating systems are checked whether the process enters into the deadlock or no. And every checkpoint status is saved in the disk. So whatever the current status of that process will be saved in the disk, and whenever the operating system detects that there is going to be a deadlock at further, if the process proceeds further, if the process proceeds further, there are chances of that deadlock can occur. So the process will be not allowed to move further and such processes will be rolled back to the previous checkpoints and that checkpoint status will be saved in the disk. So like this way we can recover from the deadlock before means after occurring it, and we can save the system going into the deadlock. So both process A, B will be checkpoints, entire state of a process stored on the disk to verify deadlock. Saves the checkpoint state in the disk After deadlock detection, the system could roll back to the last non-deadlock state, loads the state of process A and B to the last known state. So the current status will be saved of the processes, and that information of that processes will be saved, or it will be loaded. Another is kill process. Kill process means immediately you are going to stop the execution of one of the process. That means you are killing the processes, means execution you are going to stop. So mostly the low priority processes can be killed. So these processes keep on killing until the deadlock is broken. So if multiple processes are executing and all are trying to access the same resource, then there are chances that the deadlock occurs. So to avoid such deadlocks, you can kill some of the processes, like when you are presenting a PPT and in between some interruption occurs and your system has gone into hanging mode, or a system, there are chances of that system is going to into a hanging mode. So you can stop this by killing the process of PPT by pressing Control plus Alter button plus Delete button. If you press this 3 key at a time, then it will show the in task, it will show the task manager window. So in task manager you can see the list of processes, those who are executing, and the process which you want to kill, you can select that process and you can click on end task. Then that process will be killed automatically. So you can do by your own whichever process you want to kill by pressing Control plus Alt plus Delete 3 buttons at a time, or if you don't press it, operating system automatically kills the low priority processes. Next we'll see deadlock prevention. Deadlock prevention means how you are going to prevent the deadlocks to occur. So it ensures that the 4 deadlock conditions do not occur simultaneously. So in the previous session we have studied the 4 necessary conditions to occur the deadlock, that is mutual exclusion, preemption, and hold and wait, and circular wait. So if these 4 conditions occur simultaneously, then the system enters into the deadlock. So there are 2 ways for deadlock prevention in this. Methods for preventing deadlock are of 2 classes: indirect method and direct method. Indirect method is to prevent the occurrence of 3 conditions. 3 conditions you are going to prevent, like mutual exclusion, hold and wait, and no preemption. So we already discussed what is a mutual exclusion. When one process is accessing the resource, you should not allow the other process to access the resource. Hold and wait is already one of the processes using some resource. So when it is using some resource, you should not try to access another resource. That is hold and wait. No preemption, that is forcefully try to avoid the stopping of the process execution of the processes, like forcefully taking the CPU from that process. And direct method is to prevent the occurrence of the circular wait. So indirect method to prevent the occurrences, you are going to avoid 3 conditions at a time, then you can prevent the deadlock. Or directly we avoid circular wait. Circular wait directly enters the system into the deadlock, because one process is waiting for another process. One resource is waiting for another resource. So these processes and resources are waiting for each other to release, and then directly the system enters into the deadlock. So direct method is to prevent the occurrence of a circular wait. So try to avoid the circular wait so that the system should not enter into the deadlock. Mutual exclusion. So make some of the resources shareable, and eliminate and hold. So when a process requires a resource, does not hold any other resource. Eliminate, no preemption. If a process requests for a resource which is held by another waiting resource, then the resource may be preempted from the other waiting resource. That means taking the CPU from one process and giving it to another process. This is okay. So try to eliminate it so that the system can prevent in occurring the deadlock. Circular wait, that each resource will be assigned to some other processes. So in today's session, we have seen 3 methods of handling the deadlocks, and remaining we'll see in the next session. Thank you.